So, good morning, dear friends. Today we have discussed some more problems on the flexure shear capacity of the prestressed concrete beam. Now, a prestressed concrete T section beam has the following details: top flange 500 mm by 150 mm, wave 200 mm by 500 mm. The beam is simply supported over a span of 15 meter. The tendon with cross-sectional area 2000 mm square, which is parabolic with an eccentricity of 125 at the support section and maximum eccentricity of 300 mm at the center of span. The effective prestress in the tendon is 1000 Newton per mm square after considering all the losses. If the tensile strength of the concrete is 1.52 MPa, estimate the ultimate shear resistance of the support section and load carrying capacity of the beam. Now in this problem, we have taken the total span. Beam is simply supported, span is 15 meter, area of the prestressing cable is 2000 mm square. So prestressing force is equal to area of prestressing cable multiplied by stress in the cable, 1000 MPa after considering the all loss. So final prestressing force is equal to 1000 multiplied by 200, it is 2000 kilonewton, and the tensile stress in concrete, that is equal to 1.52 MPa. Now we can find out the area of the T section, that is the area of the top flange plus area of the bottom wave. It is 17.5 into 10 raised to the power 4 mm to the power 2. So similarly, as the section is not symmetrical, we can find out the Y bar. Y bar from the bottom, we have considered A1 Y1 plus A2 Y2 divided by A1 plus A2, that is from the for the top flange as well as bottom wave. So Y bar is equal to 389.2 mm and I is equal to summation of BD cube divided by 12 plus AS square. This is the standard formula. So we get the I is equal to 4.52 10 raised to the power 9 mm to the power 4. Then the cable profile is parabolic, so we can use the formula for the slope. Theta is equal to 4h divided by L square in bracket L minus 2x. Here x is equal to 0 because we have considered theta at the support. So this converted into 4h divided by L. So h is equal to total, or we can say that the net sag. At the midspan it is 300 and at the support it is 125. So 300 minus 125. So net sag is 175. So h is equal to 175 and span is 15 meter converted into mm. So we get theta, that is tan theta is equal to sin theta, that is equal to 0.012 radian, as theta is very small. Now the ultimate shear resistance of the section uncrack in flexure. Uncrack in flexure, that means it is critical in shear at the support section. VC is equal to VCO is given by 0.67 B multiplied by capital D overall depth under root of FT square plus 0.8 FCP multiplied by FT, and here parabolic cable is there, or we can say that the inclined cable we have considered, plus neta, that is the percentage loss multiplied by P sin theta. So B is equal to 200, that is the width of the wave is considered. D is the total depth of the overall depth of the section, T section, it is 650 into under root of tensile stress in concrete 1.52 plus 0.8 multiplied by FCP is equal to 11.43 and the FT is equal to 1.52. FCP is related with the P by A, prestressing force divided by area, plus neta, that is the prestressing force after losses. P into neta is related with the initial prestressing force multiplied by N, that is 2000 kilonewton, and the sin theta is equal to 0.012. So we get the VCO or VCD is equal to 350.69 kilonewton. In this case we have considered B, that is the breadth of the member, which for T, I or L beam should be replaced by the breadth of the rib or wave. So it is 200 mm. D is the overall depth of the member 650. FT is the maximum principal tensile stress given by the formula 0.24 under root of FCK. FCK is the characteristic strength 0.45. 0.24 under root of 45, we get 1.52 MPa, which is given. So FCP is also given compressive stress at centroidal axis due to the prestress, that is P by A. So P by A is equal to 11.43. So VCO is equal to V, that is equal to WL by 2. VCO is the shear resisted by the due to prestressing, and V is the maximum shear force, that is equal to WL by 2, because the beam is simply supported subjected to UDL. Here we have assumed the load factor because we have considered the ultimate design limit set method. So we have assumed the load factor as 2. Therefore it is 350.69 VCD or V divided by 2 is equal to, this load factor is there, divided by 2 is equal to W is unknown, which is required load carrying capacity, span is 15 meter divided by 2. So W is equal to 23.37 kilonewton. So the load carrying capacity of the beam is equal to W minus WD. What is W? W is the total load and W is the cell weight of the beam section. So 23.37 minus 0.175 into 24, we get the 19.70 is the superimposed load or external load, the capacity, or we can say that the load carrying capacity of the beam. Now we have taken another problem. A prestressed concrete T beam section has the following detail. Overall depth of the T section is capital D is equal to 1200 mm. Thickness of the wave is 150 mm. Distance of the top fiber from centroid is 455 mm. That is the Y bar from the centroid up to the top. And the effective depth of the beam, that is the small d, is equal to 1050 mm. Grade of the concrete is 50 M50. Effective prestress at the extreme tensile face of the beam is equal to 17.33. It is already given, Newton per mm square. Moment of inertia is also given, 60.5 10 to the power 9 mm to the power 4. Area of the prestressing steel is 2100 mm square, and FP, that is the stress in the prestress, is 1500 MPa. Effective stress in the tendon after all losses, FCP is equal to 910 MPa. Estimate the flexure shear resistance of the section using Indian IS code 1343. If the ultimate moment M is equal to 2100 kilonewton meter and shear force V is equal to 230 kilonewton. Everything is given, but we can find out the design the section for the shear. Now this is the data which is already discussed. Shear force is given, bending moment is given. So we can find out the, as per IS 1343, we can find out the moment M0 necessary to produce zero trace in the concrete at the depth, at the given depth. So M0 is equal to 0.8 FPT into I by Y. Y is also given, but this is the Y from the bottom, that's why it is 745. 60.5 into 10 to the power 9, it is the value of I. 0.8 into FPT is also already given, 17.33. So M0 is the moment or capacity of the section. It is 1.125 into 10 to the power 9 Newton mm, or 1125 kilonewton meter. Now calculate the percentage of prestress provided. 100 into area of prestressing divided by BW multiplied by D. T section is there, width of the wave, that is the bottom section, is 150 and D is already given 1050. 100 into 2100 divided by 150 into 1050, we get the 1.33%. This is the tendon or percentage of prestressing steel. Now from the table number 8 IS 1343 2012, we can find out the tau C. Tau C is the shear resisted by concrete on the basis of the percentage of steel provided. It is 1.76 MPa. The flexure shear resistance of the section, crack in flexure, is given by, crack in flexure, that means at the midspan section. So VCR is equal to 1 minus 0.55 FP divided by FP into tau C into BD plus M0 V divided by M. Now M and V is related with the bending moment and shear force due to the external load, and m0 is related with the moment capacity of the section as per this formula. So Fp is equal to 910, that is the effective prestress after all losses. This value should not exceed 0.6 times the Fp. So Fp is equal to, we can take 900 MPa. This is given, but it should not greater than 0.6 Fp as per IS 1343. So we have taken Fp is equal to 900 MPa. Fp is equal to, that is the prestress, initial prestress, that is 1500 MPa, characteristic strength of the prestressing steel. Tau C 1.76 we have taken from the table number 8. B is 150, that is the breadth of the member, and D is equal to 1050. We can find out the VCR or VC, that is equal to 308.94 kilonewton. Now, as V external shear force is less than VCR, so provide minimum shear reinforcement in the form of vertical stirrups. This is similar to the RCC. Here I have considered 6 mm diameter bar, 2 leg. So SP is equal to 0.87 Fy. Fy is related with the grade of the stirrups. ASV is the area of the stirrup divided by 0.4 B. So again T section is there, B is considered as the width of the wave. So we get 204.95 mm. But this value should not exceed 0.75 dt. Now dt is the distance where we have considered CG of the tendon from the CG of the total section, lowest value. So 0.75 multiplied by 555 is the dt. So it is 416.25 mm, and second, it should not more than 4 times BW. However, here BW is equal to 150 multiplied by 4, that is 600. So this value is already less than this one, that's why there is no problem. So provide 2 leg vertical stirrups of 6 mm diameter at 200 mm center to center at the midspan section. This is related with the beam, design of the beam for shear, crack in flexure, that is at the midspan, and if it is mentioned uncrack in flexure, that means at the support section. So this is the some guidelines given in IS 1343 as per clause number 19.6.3.2 related to the transverse reinforcement. The amount and spacing of transverse reinforcement shall be governed by shear and torsion consideration. In some beam, there is a development of torsional stresses, so that we have also considered the torsional effect. It is, however, desirable to provide transverse reinforcement in the wave when the wave is thin. If the wave is thin, then we can provide the shear reinforcement also in the wave, and cables are located in the wave. Second, in case of all members subjected to dynamic loading, eccentric loading is there, dynamic loading is there, vibration is there, in that case wave shall be provided with transverse reinforcement not less than 0.3% of the sectional area of the wave in plan. That means in the wave 0.3% minimum still should be provided. This percentage of reinforcement may be reduced to 0.2% if member where the depth of the wave is not more than 4 times the thickness of the wave. If this criteria is satisfied, then we can provide the 0.2% instead of 0.3%. These values may be reduced to 0.2 and 0.15. That means instead of 0.3, 0.2, instead of 0.2, 0.15 when high strength reinforcement is used. That means this is related with the mild steel and this is related with the HYSD bar. Third, in case of member not subjected to dynamic loading, reinforcement shall be provided when the depth of the wave is more than 4 times the thickness. Such reinforcement shall not be less than 0.1% of the sectional area of the wave in plan. The reinforcement shall be spaced at a distance not greater than clear depth of the wave, and the size of such reinforcement shall be as small as possible. And last, reinforcement in the form of link or helix shall be provided perpendicular to the line of heavy compression or shock loading to resist the induced tensile stresses. That means the provision should be perpendicular to the section. Now this is the clause number 23.4.3.1 as per IS 456 2000 and the IS 1343. At any section, if VC is less than VCR, provide minimum shear reinforcement in the form of vertical stirrups. We have already discussed and we have already provided this one. Thank you very much.